Science fiction has long tantalized us with the concept of teleportation, an instantaneous leap from one location to another. This idea of teleportation, whisking us off to distant galaxies in the blink of an eye, is an alluring prospect. However, let's be clear from the start. The quantum teleportation we're about to delve into isn't about beaming physical objects across space. Instead, it's all about the transportation of information, a concept that may not be quite as flashy as its science fiction counterpart, but is no less fascinating or revolutionary. To understand it, we need to take a step back and consider the way we currently send information, what we call classical communication. Imagine sending a letter through the post. It's a physical process, limited by the speed of the vehicle carrying your message. Now consider sending an email. While it's much faster, it's still bound by the rate at which electronic signals can travel. These methods, while efficient, do have their limitations. They are susceptible to interception, and the speed at which information can be sent is capped by physical constraints. This is where quantum communication steps in, promising to revolutionize the way we think about transmitting information. One such phenomenon is entanglement, where two quantum bits, or qubits, become inextricably linked. No matter how far apart they are, a change in one instantaneously affects the other. This, in essence, is the basis for quantum teleportation, the ability to send information from one point to another instantaneously, without any physical movement. So, buckle up as we take a journey into the intriguing world of quantum teleportation. Enter the fascinating world of quantum communication, a realm that promises to revolutionize our communication systems. Picture this. You're trying to send a secret message, but you're worried it might get intercepted. In the classical world, you'd use encryption, which is basically a complex code. But even the most intricate codes can be cracked given enough time and computing power. That's where quantum communication steps in, bringing along a strange yet fascinating phenomenon known as entanglement. In the quantum world, entanglement is a kind of superpower. Imagine two particles, let's call them Alice and Bob, separated by vast distances yet mysteriously linked. They're entangled. Change the state of Alice, and Bob instantly mirrors that change, no matter how far away he is. Now, why does this matter for communication? Well, the potential is immense. If we can harness this entanglement, we could create ultra-secure communication channels. Any attempt to intercept or tamper with the message would immediately disturb the entangled state, alerting the sender and receiver to the intrusion. It's a kind of communication that is not just faster, but also far more secure than anything we've seen before. But that's not all. The real magic happens when we pair this entanglement with another quantum marvel, superposition, where a particle can be in multiple states at once. Together, they open up the possibility for something truly extraordinary, something straight out of a sci-fi movie, quantum teleportation. At the heart of quantum communication lies a powerful method known as quantum key distribution, or QKD. This technique is like a secret handshake in the quantum realm, allowing two parties to share a string of information known as a key in total secrecy. This key is then used to encrypt and decrypt messages with the assurance that no third party can intercept the information. But how does it work? When a change is made to one particle, the other instantly mirrors that change, creating a unique and unbreakable bond. This bond is then used to generate a secret key between two parties. Now, you might be wondering, how is QKD any different from classical encryption methods? Well, the beauty of QKD lies in its resistance to hacking. In the quantum world, observing a particle changes its state. So any attempt to intercept the key would immediately be noticed, as it would alter the entangled particles and disrupt the key generation process. This makes QKD arguably the most secure form of encryption we have at our disposal. But that's not all. The world of quantum communication doesn't stop at QKD. Other protocols, such as quantum repeaters, are being developed to extend the range of quantum communication. These devices work by preserving the entangled state of particles over long distances, allowing for quantum information to be relayed without loss of integrity. With these advancements, we're setting the stage for a quantum leap in communication. Recent discoveries in quantum teleportation have shattered previous records and pushed the boundaries of what's possible. A case in point is the record-breaking teleportation feat that has been achieved over a metropolitan range. The science community watched on with bated breath as quantum information was teleported over a distance of over 44 kilometers, smashing previous records and opening up new avenues for exploration in the world of quantum communication. In a paper published in Light Science and Application, a team of scientists led by Professor Guangkan Guo and Professor Qiang Zhou from the University of Electronic Science and Technology of China, UESTC, cooperating with Professor Lixing Yu from the Shanghai Institute of Microsystem and Information Technology of the Chinese Academy of Sciences, have improved the teleportation rate to 7.1 qubits per second for the first time. Now let's talk about high-dimensional entanglement. It's a concept that might sound complex, but it's crucial for quantum teleportation. In simple terms, it's about entangling more than just two states of a quantum particle, thereby increasing the amount of information you can teleport at once. The strides made in this area have been monumental. Comprehensive research in this field has provided us with a deeper understanding of high-dimensional entanglement, paving the way for more efficient and secure quantum communication. One such step has been taken by a research team led by Ronald Hansen, a physicist at the QTech laboratory at Delft University in the Netherlands, which has succeeded in teleporting quantum information via a rudimentary network with no direct connection between sender and receiver. The team, under the leadership of Professor Biheng Liu and Professor Chuanfeng Li, has been at the forefront of experimental studies on high-dimensional quantum teleportation and quantum networks. Their notable achievements include the successful preparation of the world's highest fidelity, 32-dimensional quantum entanglement, the effective transmission of high-dimensional entanglement over 11 kilometers of optical fiber, and the development of efficient techniques for quantum entanglement detection. They have also made significant progress in areas such as high-dimensional quantum dense coding, high-dimensional quantum guidance, and high-dimensional quantum teleportation. This process of teleporting quantum information is not an easy feat. The biggest challenge lies in maintaining the delicate state of entanglement over long distances. Any interaction with the environment can cause decoherence, essentially breaking the entanglement and ruining the teleportation. The field of quantum communication is ripe with ongoing research and advancements. This cutting-edge technology is poised to revolutionize how we exchange information, opening up a new era of ultra-secure communication networks. Picture a world where your personal data is no longer vulnerable to hacking, and every single bit of information you send out is protected by the unbreakable laws of quantum physics. But the potential applications of quantum communication don't stop there. Leading scientists and researchers are already laying the groundwork for what some call the quantum internet. This would be a web of quantum connections, facilitating communication speeds and security measures that are currently unimaginable with classical internet. Now imagine signing a digital document with a signature that could never be forged. Quantum communication could make this possible too. Using entangled particles, we could create digital signatures that are inherently unbreakable. Any attempt to tamper with the signature would disrupt the entanglement and reveal the intrusion. In the grand scheme of things, we're still in the early days of quantum communication. There's so much we don't know, so much yet to be discovered. But one thing is clear. This technology has the potential to transform our world in ways we can't even fully comprehend yet. That's what makes this field so exciting. Quantum communication and teleportation are just the tip of the iceberg in the fascinating world of quantum mechanics. What we've discussed so far is a mere ripple on the surface of the vast quantum ocean. Yet, these ripples signify an evolution in the way we understand and utilize information. In conclusion, quantum communication and teleportation represent a revolutionary shift in our approach to secure and efficient information exchange. They form the stepping stones towards a future where quantum mechanics is not just a scientific theory, but a practical tool that shapes our daily lives. The world of quantum mechanics is vast and ever-evolving. It invites us to question, to explore, and to innovate. So, I encourage you, dive deeper, explore further, and embrace the exciting possibilities that quantum mechanics holds for us.